Hello and welcome to Toddcast number 32. Sorry for the sound difficulty if that just happened. Um, but one covered this in this one, reaction diagrams and mechanisms. And the reality is all the thermal review and kinetic reviewing we did, this Toddcast pretty much covers the crux of what you need to be able to read and interpret for organic chemistry. So again, not as mathematical as GChem was, won't really do calculations, but you will have to be able to look at a graph and have an understanding of what's going on in the reaction. And so reaction mechanism, we're going to start into those, and they're going to become a major part of the organic chemistry class. Every reaction we look at, we're going to worry about the mechanism. How does it happen? And so a mechanism is a stepwise from starting materials through whatever transition states and intermediates occur along the way to the final product or products, if they're side products, that occurs in a reaction. And so by understanding the mechanism, you can learn the nuances of how to manipulate it to get a higher yield or possibly enhance the formation of a different side product by changing the nature of the reactants or the solvent. And so we're going to use energy diagrams to understand the mechanisms and the mechanisms to understand how to manipulate the chemistry. So we start with the simple one-step reaction. You hear terms like a concerted reaction. So where that phrase comes from is a concert, everybody's playing together. So concerted, everything happens at once. And so when this happens, I'm going to do a diagram of the free energy, going to be in kilojoules per mole, the standard unit. I'm not going to bother really marking too much on my axis because I'm worried more about what the actual nuances of the reaction are. So one step, it all happens in just one. They come together, they do what you need to do, and spit out the product you need to get. So the things you have to note. The start of it is going to be right here. And it's going to go through what's known as a transition state on its way to forming products. So from the previous podcast, we emphasized the fact that higher energy in the beginning, lower energy in the end means energy is released. So this would be a favorable reaction because delta G is a negative number. So that you have to recognize that, and then activation energy is about the same as delta G. So we really don't need to put a lot of heat energy in to make it go. We can probably do this at room temperature, maybe even cool it down if we need to. So that's my previous knowledge. I want to make sure I understand what each part is. So again, we do not call it time because unlike time, the reaction can go forwards or backwards. Time can always only keep on marching forward. It'd be nice to go back in time at some points, but the reaction can go from the starting materials to the final materials. But because it can go backwards, we call it a reaction coordinate. So it's over the course of the reaction, early, middle, and late in the reaction, but not necessarily a time log. Okay, so starting material is anything that's in there, a reactant, another reactant, a catalyst, anything that's involved in the reaction are your starting materials. The products we represent in P, that's all products. Side products, the product you want, any offshoot, some fragment that falls off that is kind of useless to us, but it's still a product in the end. And then the key thing up here is something called the transition state. So transition state is something you know had to happen, but it's so instantaneous and so brief that you cannot actually observe it with reliability. So in other words, its lifetime is too short to have a distinct observation, but we know it had to happen. So a really good example, if you throw a ball up into the air and it comes back down and you catch it, you know, gravity is acting on it, it goes up, it's going to gradually slow down, slow down, slow down until it reaches its apex, its highest point, in which case it has no velocity in the y direction, no speed going up, and then it falls back down. But if you can actually see when it reaches that highest point, like precisely see which way the ball is lined up, where the laces are, where the valve stem is, whatever kind of ball it is you're throwing up, if you can precisely see it, that'd be really impressive because it generally happens so fast that we don't see it. So same thing here. We know it had to happen. We know at some point the ball had to stop. because it changed directions. Here we know it had to go through transition state because it changed composition, but we can't see it. It's short-lived. So they come together, they form some sort of interactive species between two reactants called the transition state. It kicks out whatever it's going to kick out, and you end up with a product in the end. So we'll go over this many times over, but just in a one-step reaction, passes through a transition state. Okay? Again, why do we call it a reaction coordinate and not time? It's because it can go backwards, time cannot. And then starting materials and not reactants because you could also have a catalyst in there. So something to keep in mind. And then transition state. Transition state is a short-lived logical intermediate. No, not an intermediate because intermediates have a finite enough time that you can actually measure them. You can use spectroscopy to determine their presence. So it's something that's so short-lived as it passes from one state to another that we can't confirm it through spectroscopy, but we know it has to happen. We know it has to do that because there's no way it could have arrived at the product without passing through a certain way. So again, we'll emphasize that with specific reactants we go, but it's the passing point, the highest point here as it passes from reactants to products. Okay, if it's a two-step reaction, okay, that's going to be a little bit different. Now we will have an intermediate. So notice it looks very similar. You have starting materials and products, just like you did before. So starting material, product, seems okay. But now you have a transition state, and it goes to form some intermediate, and then you have a second transition state. So transition state 1, transition state 2. So a good example is if I have I'm going to put T-butyl because it's tertiary. T-butyl, let's say bromide, some group like that. And it reacts with something like methyl sulfide or methylthiol. Then what will happen is first, in this part from here to here, this will leave, and the rest of the structure will reform to turn into H3C, H3C, and H3C in a planar configuration. So this was tetrahedral. I didn't draw it accurately, but it is. When it leaves, it becomes trigonal planar. So it takes energy to break a bond, but you get a little bit of energy back when it rehybridizes from sp3 to sp2, and you have less steric hindrance. It's more stable. Okay. The second part of the reaction is where the thiol nucleophile is going to come in and form a new bond. So as they get closer together, that's your transition state going up. And then once it reconfigures and you form that new bond, formation of bond releases energy. So your initial increase in energy is just this has to go back to sp3, this has to experience some crowdedness until the bond starts to form. Okay, so this is actually relatively low energy. It doesn't take much for it to go. So it leads to a question, which step is the rate determining? Well, you should be able to tell. Number one, this is a really big climb from here to here is the activation energy for the first step. That's a lot of energy. Second one, not so much. So lower transition state, easier to get to. So the rate determining step is the one that's slowest. The one that's slowest is the one that takes the most energy. So first step is rate determining. Okay, this is an SN1 reaction. Mentioned it in a previous Toddcast, alluding to it in this one. We're actually going to cover it thoroughly in about 5, maybe 6 more Toddcasts. It'll pop up. So just want to give you some hint as to what it is. And then how are transition state and intermediate different? Well, transition states, they don't have a long enough lifetime to measure them, to analyze them, to do spectroscopy on them. An intermediate has a short enough lifetime. And then generally speaking, the deeper this well, the more stable the intermediate, the longer it has for a half-life or a period of time of existence. Okay, so knowing your energy diagrams, recognizing one step, two step. This is a two-step reaction, and it only depends, the rate determining step only depends on the electrophile, leaving group leaving. So that's why we're doing so much kinetics before. Okay, other things that we worry about. The impact of a catalyst, the whole purpose of a catalyst is to lower the activation energy. So if this was my one-step reaction, my conservative reaction pathway, and I didn't want to heat it up because maybe the compound's unstable, or with heat it can denature or form the wrong product, then we typically represent catalyzed reaction the altered reaction by the dashed line. And notice it has a lower energy transition state because the catalyst is now part of that transition state. So it helps to align the reactants. So by themselves, they have to find each other and line the right way. Catalysts combine them and start weakening the bonds that need to be broken and align whatever's reacting the correct way so it can react faster and with less invested energy. The catalyst is doing the work, a little bit of the work for you. Okay, so starts at the same energy, finishes at the same energy. So as a result, delta G is not affected. The catalyst has no impact on the favorability. If the equilibrium constant is, let's say, 1,000, it stays 1,000. If the delta G is negative 48 and stays negative 48, has no bearing on it, but it does affect activation energy. And in doing so, it makes the reaction faster. So, as mentioned, no change in the thermodynamics, but a change in the kinetics. Faster reaction, but same products. Okay, another thing we can do, we look at this. We can see what happens when we have two reactions. So that's occasionally the two reactants can form different products. And so the dashed one doesn't represent catalyzed, even though I hinted that last time that's how you represent it. In this case, I did it, probably should have used different colors. But in one reaction versus another reaction, I'll redo this line in red to emphasize that it's not catalyzed, just a different pathway. The red pathway has a lower activation energy, so it can occur faster, but the product isn't as stable. Black pathway takes more energy, but you get a more favorable reaction. So when you have two competing reactions, you can actually change the reaction conditions to favor one over the other. This is going to be known as either kinetic control, if I choose, or whatever I do is choosing the pathway in this region, the kinetic region, or thermodynamic control, where I look at this part, decide which one I want to get. So if I do it at very low temperature, then it doesn't have enough energy to overcome the activation barrier. It will favor the red pathway. And that's simply because it does not have enough energy to overcome the black pathway. At high temp, you can choose either pathway. It has more than enough activation energy. So it chooses the black pathway because you get the best results. So this would be known as kinetic control. The lower one is known as thermodynamic control. Okay, so just how we represent our reactions. Okay. That said, A plus B going to Q plus Z in one case, or A plus B going to different things. So let me get rid of my writing. So this can come in. So slow reaction generates more stable products. So the one slower meaning higher pathway, so it doesn't go as fast because it's higher activation energy. So slower path is the black one. Whereas the faster reaction gets Q prime and Z prime. Similar products, but different results. So the red pathway Let me redo that. Gets the so-called kinetic product. So temperature again, if you go with low temp, you kind of force it to go the lower pathway. Give it high temp, you can choose either one, so it chooses the better pathway. Okay, a different way of competing reactions is one where the red pathway is both less favorable and slower. There's no reason in the world you would ever want to do this. So the red pathway leads to a side product. It's just random that every now and then it'll happen. But if you raise the temperature, the more you raise the temperature, the more you can push it up that pathway, but you'll never see a large amount of it. But you might see, let's say instead of 2% impurity, you might get like 6 or 7 or 8% impurity. And maybe that impurity is what you want. So maybe it's worth it to do that. So in that case, fast reaction generates more stable product, E and J, and the slow reaction also generates, or I should say the faster reaction, but also the more stable products. And then the slower one generates the less favorable E prime J prime. Okay. So hardly any other side products. Okay. Last thing I want to emphasize is something called the Hammond plot or Hammond postulate. I'm looking at the Hammond plot, something different. My apologies. Hammond postulate, which basically says the transition state reflects either the starting reactant or the product more so according to its relative energetics. So I've said a lot of words to simply say this is high in energy. So the reaction goes through transition state earlier. The transition state is more like reactants. The dash one, very high activation energy, and it's an unfavorable reaction. So it's going to actually be more like the product. So the transition state is closer to the state of the product. So when we draw these diagrams, they do not go the same way like this. It's a transition state at the same point. You have what's known as an early transition state when it's a highly exothermic reaction, and you have a late transition state when it's endothermic and you have relatively high activation energy. So just Hammond postulate is that your transition state will reflect the species it is closest to in energy. So transition state, if it's closer to the starting material than the product, it'll be more like a reactant. Transition state is closer in energy to a product than a starting material, will occur late when it's closer to the end of the reaction. So the timing transition state is such that it occurs closer to the more stable compound. So that's not exactly what it means. So just go back with what I said before, is that it's going to be, transition state will be closer to the one that is most similar to an energy. Okay. Early transition state, late transition state. Structure and transition state is more similar to the structure and then probably most similar to in terms of energy. That is the true. That's what we're going at. So that this is the statement I want you to have. Okay, so want to look at a reaction mechanism. That's where this is where everything's going. So everything we've done to this point has been sort of giving us information to finally come up with some sort of, I don't know, perspective of how to look at reactions. So we're going to learn different reactions. They're going to be things called addition, elimination, substitution, electrocyclic, just a series of different reactions. And so substitution, as the name implies, one thing is substituting for another. So if I have this reaction and R's represent some alkyl group, could be CH3, is H2CH3, cyclohexane, could be something on there. Same thing here, but the key thing is this is the reactant here. This is going to be called a nucleophile. Nucleophiles typically are negative or partially negative, and they have to have a lone pair. They have to be a Lewis base because they have to donate a lone pair. The electrophile, on the other hand, has a delta minus delta plus. It's called the electrophile because it has a love for electrons. And the nucleophile, love for nucleus. So the nucleophile is going to come in and attack the delta plus. So just like arrows with resonance, we draw starting from where the electrons are to where they finish. So this means there's going to be a new bond between nitrogen and that carbon. That's a fifth bond to carbon. So that bond has to send the pi electrons up to the oxygen. Okay, I'm going to get rid of my purple line. Let the computer generated one come in. So when it does this, we now have an intermediate. So this is what we mean by an intermediate, so that we now have this R group that was there in the beginning, the Cl there in the beginning. This O just became an O minus. It'd be complete by putting lone pairs on it. And then the nitrogen gave up its lone pair and now has a positive charge. Okay, you don't want charged species. You cannot resonate over to stabilize anything. That's not going to help. The O is not going to donate to an N, make a new bond, because that would be too many, just too many bonds to nitrogen at that point. It would have a fifth bond. So what has to happen is these electrons are going to kick back in, and one of these three things has to get kicked out. It ends up the weakest bond is a carbon-chlorine bond, so that's what's going to be called a leaving group. So the chlorine is a leaving group. So when those electrons kick back in, notice they kick back in into the middle, which means it's making a bond. So it's making a pi bond. And these bonding electrons ending up on chlorine. So chlorine is going to go off and form 1, 2, 3, 4, 6, 7, 8, and a negative charge on the chlorine. And I should put the charge where it belongs. So chlorine comes off as a leaving group. That is your mechanism. It follows the flow of electrons. So what I get from this, I know that it has to attack the carbon, the delta plus. So if this gets really, really big, I know this looks like a crowded space. It's going to be a little bit harder for the reaction to occur. So there's certain things I can know from this mechanism. If it has to squeeze into this one spot and break a pi bond, then I know the pi bond is stronger. It's going to be harder to react. If this gets bigger, it's going to be harder to react. If I know the mechanism, I can start making predictions. What if I change one thing or another thing? How can I make this happen faster, better, at a higher yield? I start making predictions on how the reaction will go based on how I change slight things about these two structures. Okay, addition across a carbonyl. Okay, so substitution, we had the nucleophile go in and the leaving group come out. So somebody goes on, somebody comes out in a substitution at a sporting event. Group comes in, nucleophile goes in, leaving group comes out. Substitution. Addition means you're going to add it. They're going to be added together. So these two things are going to end up as one compound in the end. So in addition, the things add together. Two reactants going to form one product. It's going to be very similar. And I'm going to put a lone pair on the nitrogen. But this is where you have to make a decision. The lone pair on carbon carries a negative because of formal charge. Nitrogen has no negative. Nitrogen is more electronegative, so it's going to hold on to its electrons. So if this thing attacks, it's going to be the carbon nucleophile that's going to come in. It's going to do the same reaction it did before, but now the difference is carbon-carbon bonds are strong, carbon-carbon bonds are strong. So if this O wants to come in, it can't do it. There's nothing to kick out. Alkyl groups, carbon-carbon bonds can't be broken. Carbon-carbon bonds, hard to break. Carbon-carbon bond, hard to break. So there's no leaving group this time. So with no leaving group, nothing that can be kicked off. It's going to be stuck there. So it has to pick up something from the solvent. And so typically, HCN will be, you carry this out in some solvent that has to be able to give up an H. So somehow, some way, this interacted with perhaps an HCN. So I don't know exactly what it reacted with, but that's as good a candidate as any. So that lone pair went there. that regenerated the same CN minus it was on in the beginning. So you use CN minus and HCN in combo so that the CN can go on, and then it can pick up the H and regenerate the CN nucleophile, the cyanonucleophile. So your mechanisms, the arrows represent where electrons start to where they finish. And so this H plus, again, I'm going to assume it comes from an HCN, but we'll have to know the specifics of the reaction. And depending on what I use as the acid, I can make the reaction go more efficiently, less efficiency, more side product. I can start messing with the group a little bit. We'll learn as we go. But for now, mechanisms, all those rate studies and all the energy diagrams that we generate can give us a prediction on how these reactions will go. So that covers our first step into mechanisms. Enjoy, because you'll be doing them a lot. So this ends this Toddcast, and also kind of ends just, I don't know, the review portion of all these Toddcasts. So we're about halfway through the Toddcast. So from this point on, everything becomes fresh new material, reactions, reaction mechanisms, synthetic pathways, just all the rules of OChem and the reactions you have to understand. So we've officially left review stage, and now we're going into let's learn the new material. So hopefully this went well, and I will see you at the next Toddcast.